I'm Andre from the High Performance Academy, and I want to welcome you back to the second in our series of free tuning lessons. Now, in our last lesson, we looked at the fuel delivery and air fuel ratio on a Nissan 350Z running an AEM Infinity ECU. And at the time, I said to you that there's really only two things we as tuners are trying to do when we take away all of the advanced features that these new ECUs have and new engines have. One of those things is we're tuning the fuel delivery through the fuel injectors, and the other part of our job is tuning the ignition advance or ignition timing. So in this lesson, we're going to look at that second part, which is the ignition timing. Before we get into that though, we need to discuss a little bit about what we mean when we say ignition timing or ignition angle. So obviously we need something to begin the combustion event, and the aspect that does that is obviously the spark, jumping the gap in the spark plug. And the point during the engine cycle where that spark occurs is really critical to both the performance of the engine as well as its reliability. And the point that that spark occurs in the engine cycle is the ignition advance angle. Now, we need a way of referencing that or talking about what that ignition angle actually means. And to do that, we need to discuss briefly the four-stroke process. So that's the principle behind which most internal combustion piston engines operate on. And the point that we're going to reference is where the piston is at the top of its stroke on the compression stroke. So it's already inhaled a new charge of fuel and air, the valves have closed, and the piston's moved up to the top of the bore. Now, when it is at the very top of the stroke on that compression stroke, that point is called TDC, which stands for top dead center. So we consider this point to be the 0 point in when we're referencing our ignition angle. So our ignition timing or ignition angle is referenced relative to that point in the engine cycle where the piston has reached top dead center. So generally, when we're talking about ignition advance, the ignition advance angle will be in degrees of crankshaft rotation before top dead center. So we actually normally start the spark event as the piston is still coming up towards the top of the stroke during that compression stroke, as it's compressing that new charge of fuel and air. So now we understand a little bit about the terms. Let's have a look at a diagram that explains exactly what's going on inside the cylinder. So here we have a graph of the pressure inside the cylinder as we move through the combustion cycle. So on the left axis here we have our combustion pressure. So this is the actual pressure being measured inside the combustion chamber. Across the bottom axis here we have our ignition angle, and you can see that we've referenced this 0 degree point here in the center. Now that 0 degree point, that is that point I just discussed, TDC or top dead center. That's the point where the piston is at the top of the stroke. So we actually start the process over here on the left hand side, and the piston is moving from the bottom of the stroke up towards top dead center and compressing that fuel and air charge. I've got 3 points demonstrated on this graph, and we're going to talk about each of them individually, but you can see that as we move to the right here, the pressure being measured in the cylinder naturally starts to increase, and that's simply because as the piston compresses that fuel and air charge together, the pressure naturally rises because it's got nowhere to go. Remember, the valves at this point are closed, and as the piston moves up the bore, the volume of the combustion chamber or the area above the piston, including the combustion chamber, is decreasing as that piston moves up the bore. Now we're going to start by talking about this point B. Now for this particular point of operation of the engine, point B is actually our correct ignition angle, and in this case point B is 20 degrees before TDC. So the ignition event has occurred 20 crankshaft degrees before the pistons reach TDC. Now, most people, when they think of a combustion event, they think that when the spark occurs, that fuel and air charge explodes in the cylinder, much like a stick of dynamite. Now, that's actually not the case. Under normal combustion, we actually get a relatively slow combustion event or slow burn, and what happens is we get a flame front that starts propagating out from the spark plug. Now, as it moves out through the combustion chamber through the cylinder, that flame front will ignite the fuel and air ahead of it, and what we get is a nice, slow, gradual rise in our pressure. And you can see that that's exactly what's occurring here. Our pressure continues to rise even after the piston has moved past top dead center, and it's starting to move back down the bore. And you can see that our pressure peaks, and it's peaking at around this point here, which is somewhere around about 16 to 18 degrees after TDC. So 16 to 18 crankshaft degrees after the piston has started moving back down the bore. Now the critical point of this is the amount of pressure we have acting on the top of the piston, and we want to start our ignition event so that we achieve our peak cylinder pressure around about that 16 to 18 degrees after TDC. If we can achieve that, the angle through the connecting rod and into the crankshaft is going to make the most mechanical advantage of that pressure acting on the top of the piston. That's going to result in us seeing the most amount of torque possible at the crankshaft, and with that also comes the most amount of power that we can get. So when we're tuning the ignition advance angle, this is what we're trying to do. We're trying to achieve our peak cylinder pressure and get it to occur somewhere around about that 16 to 18 degree after TDC mark. So that's what it looks like when we get it right. Now we're going to look at two examples where we've got the ignition timing wrong. We're going to start now with point C. Now in point C, we've started the ignition event too late. In this case, we're only 13 degrees before TDC, and we call this a retarded ignition event because the ignition event has started too late. Now in this case, there's not enough time for the pressure to really start peaking before the pistons move past TDC and move back down the bore. So what we get is this expanding fuel and air charge being burnt, but it's expanding about the same rate that the piston's moving down the bore. So we get this flame front literally chasing the piston back down the bore. As you can see from this drawing here, we don't have anywhere near the pressure that we had at point B. We've only got around about half the amount of pressure that we had in point B, and that's all we've got acting on the top of the piston. Conversely, we don't see as much torque reaching the crankshaft, and we're not going to make as much power. So that's what happens when we've got a retarded ignition event. Now let's have a look at what happens when we have the ignition event happen too early. In this case, point B, in which case we've started the ignition event 35 degrees before TDC. In this case, we call this an advanced ignition angle because we've started the ignition event too early. So when we do this, what we see is that the combustion event has the pressure in the cylinder rising quite sharply while the piston is still moving up the bore. Now this is counterproductive because we've got that pressure in the combustion chamber in the cylinder working against the piston while it's still trying to come up the bore. Now that's counterproductive to the engine producing torque, so that's not what we want to achieve, and when we do this we're not going to see as much torque or as much power. Now the other effect that's being demonstrated in this particular drawing is you can see we've got some sharp spiking in our pressure trace here. Now this is indicative of a phenomenon called knocking or detonation. Now remember I said under normal combustion we get a nice smooth flame front and we get a nice smooth rise in our pressure. When we have knock or detonation occur, what's happened is that the pressure and heat in the combustion chamber has become so great that pockets of fuel and air around the outside of the combustion chamber spontaneously combust. Now when that happens, this is exactly like a stick of dynamite exploding in our cylinder. We get a very sharp spiking in our pressure, which is shown here, and that sharp spiking is very dangerous for our engine. It can damage the pistons, it can damage the cylinder head, it can also damage the con rods and the crankshaft. So we need to stay away from that. Okay, so now that we've explained what is actually happening when we're tuning our ignition advance, we're going to have a look at a quick demonstration on the dyno. Now, the graph that I've just shown you is measuring the cylinder pressure directly in the combustion chamber. Unfortunately, unless we're working for an OE manufacturer or a very well-funded race team, the chances are that we're not going to have access to this data. but instead remember the whole reason we're tuning the ignition timing is to optimize the torque. And if we're on a proper load-bearing dyno, we're going to be able to measure that torque. So we're going to have a look at optimizing the ignition angle on our mainline chassis dyno. Now, for the purposes of this demonstration, we're using a turbocharged Toyota 86 fitted with a Motec M1 ECU. I just want to take a moment to explain that it doesn't matter what sort of engine you're tuning, whether it's a 4-cylinder, a V8, whether it's naturally aspirated or turbocharged, or whether you're using a Motec, a Haltech, an AEM, or you're reflashing the factory ECU. But remember, it's the core principle of the ignition timing that we're going to be talking about and looking at here. So it's applicable regardless of what platform you're tuning on. So let's just drop into our laptop software here, and here you can see we have our ignition table in the Motec M1 ECU. Now for this demonstration, I'm going to be running the car in 4th gear, and we're just going to look at tuning one area of the map at 3,500 RPM. Now before I got started, you can see what I've done here is I've highlighted a section of cells in the table, and I've set them all to 20 degrees of ignition timing. So remember, that means that our ignition event is happening 20 degrees before TDC. Now what I'm going to do is we're going to use the torque optimization function in our mainline dyno, and what this will do is it will plot the torque being measured by the dyno as we vary the ignition advance. So we're going to start that now, and all I'm going to do in the laptop software is I'm just going to highlight all of the cells that we're running in, and I'm just going to advance the timing. And as we advance the timing, the dyno will plot how the torque is affected by the ignition advance. So we're just going to do that, and we'll step through the ignition table until we see the torque peak. And what it should do is it will peak, then it will plateau, and finally if we keep advancing the timing further, it will actually end up dropping off. So this is the effect that we see when we're tuning the ignition timing, and what we're looking for is the ignition angle where the torque first peaks. Now that point is known as MBT, which stands for maximum brake torque timing, also is known as minimum timing for best torque. And we can see that now on our dyno screen, our torque has peaked at 82 Newton meters, and as I continue to advance the timing, you can see that our torque is now actually dropping away. So we've gone all the way up to 50 degrees of ignition advance, and you can see that the dyno has shown us that we reached our peak torque value here, and that peak torque value was reached at 42.4 degrees of ignition advance. I'll just stop the car running on the dyno, and as I do that you can see that the dyno continues to redraw our torque dropping down. So that's a really powerful way of demonstrating exactly what's going on as we advance that timing, and that's always what we're looking for, that point in the ignition advance where we first reach our peak torque, that MBT timing point. Now of course, when I'm tuning a car on the dyno normally, and I'm not presenting a lesson like I am here, I'm always going to be listening with an audio knock detection system to make sure that the engine is not knocking or detonating. We must make sure that we stay away from any knock or detonation that's going to destroy our engine very quickly, and particularly in an engine that is running on pump gas, particularly a turbocharged engine or one with a very high compression ratio. Often the engine will actually begin knocking or detonating while our torque is still increasing, in which case we call this engine knock limited, and it's that knock threshold, that point where knock occurs, that we have to limit our ignition timing to. So that completes our lesson, and I hope that you've enjoyed it, and I hope that you've learnt something. If there is something specific that you would like us to cover in these lessons, please feel free to ask in the comments below. Now, in our next lesson, we're going to be looking at how the air-fuel ratio we choose will affect both the power the engine makes as well as the reliability of the engine. And you'll see that in your email inbox shortly. Thanks for watching.